Okay, so we've talked about messages in the abstract. I've talked about conceptually how they can be like sending a letter or making a phone call. And I've also given a sort of a diagrammatic representation of how send and receive work, but we've not talked about any actual syntax. So I'm going to talk about real syntax here to show you how you actually send and receive. So please ask again, please feel free to ask questions as you go along, just so if anything's unclear. So in MPI, a message contains a number of elements of some particular data type. So that is, as I said, your fundamental mental model for a message is 5 integers, 6 double precision numbers. Now, MPI has built-in data types called basic types, and we'll see that they correspond to the language data type. So MPI knows implicitly how to send integers, characters, double precision numbers, floating point numbers, and stuff like that. However, we can actually build up derived types. Derived types can be built up from basic types. And this allows you to do more general things. In particular, it allows you to find things which look like structures, which have mixed type, or to send subsections of arrays. We'll see that by default, you can just send a single block of data. If you want to send more complicated patterns, you can use derived data type. This lecture is going to be given by Mark tomorrow. I'm not able to give that lecture, so you'll have relief from me droning on for 2 days, and someone, Mark, will come in and give you that talk. And I'm just going to talk about derived types for now. Now, this is one of the few places where C and Fortran, the C and Fortran interfaces for MPI differ, because of course C has different types from Fortran. So it's a very basic difference, but not a big deal. So it turns out that in MPI, we don't have an MPI send float routine, MPI send int routine, MPI send character routine. We have a single send routine, regardless of the data type. Now, because it's a library routine, we need to tell MPI what the data is, because when we pass an array or a pointer, the function that's being called doesn't know what the data type is. Languages like C and Fortran don't dynamically pass type information. So whenever we send a message, we have to tell MPI what the data type is. So for every data type in the language, there's a built-in data type, a constant in the header file, which you can use. And this will become more obvious when we see examples. But for example, now MPI has all these data types, but the only ones as a scientific and technical programmer you'd ever use are integers. Okay, so if you declare an integer, you have to tell MPI it's an MPI int. Float, MPI float, double, MPI double, and maybe characters, MPI char. There's lots of other stuff here, but so for every language type, there's a built-in MPI type. Fortran has a different built-in set of data types, more tailored to scientific and technical programming: integers, real, double precision, complex, logical, and character. So if you want to send an integer, you say MPI integer, a double precision, MPI double precision. I would very, very much advise Fortran programmers to stay away from character arrays. Character arrays in Fortran are weird, in my opinion. They're too clever. It causes immense. A character variable of length 6 is not the same as an array of 6 characters. It gets very complicated. I just stay away from characters after in Fortran. It's a bit of a. But I only ever use integers, double precisions really as a Fortran program. So that will become more obvious when we see some actual examples. Point-to-point communication. So in point-to-point communication, it's communication between two processes. Now, as Monica asked in the first lecture very early on, can we do more general things? Yes, we can do collective communications like broadcasts and reduction operations, but they will be covered in a separate lecture. We're just doing point-to-point at the moment. And this, point-to-point communication is the absolute fundamental concept in MPI. If you understand this, then the rest of it all makes sense. So it's a communication between two processes. It takes place within a communicator. Two processes must be in the same communicator for the message to be sent. Now, if we use MPI COM World, everybody is a member of MPI COM World, and therefore it's a moot point. But we will talk about how you can do more clever things with communicators later on. But for now, whenever you see communicator, just put MPI World. So it's a two-sided process. The source process sends a message to the destination process. The source process issues a send routine. The destination process has to issue a receive routine. The communication takes place within the communicator, and the destination process is identified by its rank in the communicator. So this rank is, as we said, we run a program here on 6 processes, so we know the ranks are numbered 0, 1, 2, 3, 4, 5. So it's a very easy, and that's true in Fortran as well. I should have said that before. This will confuse Fortran programmers. It is confusing, unfortunately, but you know, the ranks start at 0 even in Fortran MPI. So point-to-point messaging in MPI, let's get some terminology. The sender calls a send routine, and we see there are multiple send routines, for example, corresponding to synchronous and asynchronous send, specifying the data that is to be sent, which is typically an array or a vector. This is called the send buffer. So the sender says, here's the data I want to send. It's an array of 50 integers. MPI calls that the send buffer. The receiver decides independently where to receive the data. So it specifies where the incoming data should be stored, and this is called the receive buffer. So when you receive a message, you say, I would like to receive a message, please, and here's where I want it to be put. And the data goes into the receive buffer. However, as someone already pointed out, a message has more than just its data. It has envelope header information, metadata, like where it came from, how long it is. This metadata is metadata describing the message is also transferred automatically, and you have to receive this into separate storage. So the sender specifies a single buffer. This is the data I want to send. The receiver specifies 2 storage locations. One is the receive buffer. The other is for the metadata, and this is called the status. Okay, so the data goes into the receive buffer, and the metadata goes into the status. So there are a number of communications modes. So the obvious ones are synchronous and buffered. In MPI, synchronous send is by definition synchronous send. It only completes when the receiver has completed. It's like making a phone call. You could also do an asynchronous send, and MPI calls that a buffered send. That always completes unless an error occurs, irrespective of the receiver. In other words, it's like sending an email or posting a letter. You fire and forget. Now, if you think about it, I'm writing a program. I declare an array X. It's a megabyte long. Okay. I then send that asynchronously to someone. I said, here's a megabyte of data. I want you to send it to somebody else. Don't tell me when it arrives. Just send it. Okay. That's an asynchronous send. But what's the problem there? Okay. That means I do not know when the data has been sent. So there's a problem. Okay. So I declare when. That's what I'm saying here. An array of 1 megabyte. I issued an asynchronous. I don't know if when it's received. What's the problem? What am I going to want to do with that data later on? Am I going to just leave that data untouched for the rest of the program? So I've declared an array of 1 megabyte. Am I just going to leave it untouched for? Seems unlikely. I don't want to hazard a guess. I mean, I'm going to want to exactly, absolutely collect it, overwrite or deallocate. Absolutely can. Overwrite, redeallocate the array. But how do I know? I don't know when I'm allowed to do that because I don't know when if the data has been sent or not. So what is the only way that you can implement an asynchronous send safely? What does MPI have to do for these asynchronous sends? And the hint is in the name, possibly. Copy, absolutely. So that's very well. So the reason that MPI calls it buffered send is to make it clear to you MPI is going to take a copy of this message. So asynchronous sends are called buffered send by MPI to tell you the only way you can safely implement an asynchronous send is to take a copy of it. It is buffered somewhere, okay? And that causes quite a few technicalities. I'll come back again. Now, standard send is what most MPI programs will use. The problem is it can be either synchronous or buffered, and that causes endless confusion. So I have a whole lecture immediately after this one to try and explain what the rationale behind that is, okay? So that is important to realize it can be either synchronous or buffered. So for that reason, when I say do a send, I recommend you use synchronous send because we know what synchronous send does. It is like making a phone call, okay? Receive completes when a message has arrived, and receive is always synchronous. When you issue a receive, it waits, okay? So it's a bit sad. It's like if you're expecting a phone call from somebody in the MPI model, you go and stand by the phone and wait for the phone to ring. If it never rings, you stand there forever. There are ways called of getting around that problem, but by default, receive will wait forever. Is that clear? Synchronous send is after we describe synchronous, it's like making a phone call. Buffered send is asynchronous, like posting a letter or sending an email, but MPI has to take a copy of it. That's why it's called buffered. Standard send can be either synchronous or buffered. You don't know which. Sounds a bit weird, and I'll try and explain why that is. Receive completes when a message has arrived, and it's synchronous. You just wait. So the MPI sender mode, standard send is MPI send, synchronous send is MPI send, buffered send is MPI Bsend, and receive is MPI receive. So I would recommend, and I can explain this later, that in all the exercises, when I say send, use MPI send. It's the cleanest, simplest one. You know what happens. You issue a send, you wait, there's no copy taken, you wait for the receiver to pick up, and then the data is transferred. So this is the cleanest and safest, I think, method to use. I'll explain why in the next lecture. So one of the most unfortunate things about MPI is that standard send can be either synchronous or buffered. It is quite confusing, and it's a shame that this is about the third lecture and we have to mention this, but it is. There are reasons for it, and I will try and explain them. So MPI send, MPI send, which I recommend you should use, MPI Bsend, and MPI receive. So how do we send the message? Well, this is the prototype. I'll give you an actual example later on in the next slide. MPI send, we have a buffer, that's our send buffer. It has count data types, 10 integers. It's a destination where it's going. We can tag it, and we'll come back to the tag later on. And MPI com, the communication is taking place within a communicator, and for the moment we'll use MPI com, we're onto there. In Fortran, it's MPI send, buff count data type, dest tag com. I are exactly the same, except this is a pseudo syntax. This is saying, so in Fortran, it is illegal, well, it is illegal to have a Fortran routine which takes a data type takes an array of undetermined type. Okay. In C, you just say void. It's anything. Fortran is very strict, so technically you're not allowed to do this. However, you get away with it. So this is just saying, look, buff can be of any type. Now, technically, that's illegal Fortran, but everyone does it. So we just, you just have to, as a Fortran programmer, you just have to look away at this point. But the syntax is the same. Buff count data, dest tag com IR, except you have an IR on the end as opposed to being the return code. Maybe easier if we see a specific example. So I want to send data from rank 1 to rank 3. So in the program, I declare a normal array, int x10, and then I say MPI send x, it's 10. I have to tell MPI what the data type is because it doesn't know. It's an MPI integer array. Dest is 3. Tag is metadata. Tag is like a colored envelope. Normal letters come in white envelopes. Bills come in red envelopes. You can specify a small piece of metadata when you send a message, and it's the tag. And typically tags aren't very heavily used in MPI, but they are there. Okay. So I want to send data from rank 1 to rank 3. If I ran this program, is that what happens? What does this, imagine I run this program on 4 processes. So I do MPI run minus N4 or S run minus N4, this program. So I have rank 0, rank 1, rank 2, and rank 3. I want rank 1 to send data to rank 3. What does this program actually do if I run it as written? Who does the send? All processes send, absolutely. So what will happen? What's guaranteed to happen in this program? In particular, process 3 will try and send to rank deadlock, absolutely. Process 3 phones itself and goes, why am I engaged? And waits forever. So this program is guaranteed to deadlock for 2 reasons. A, everybody's calling send and nobody's calling receive. But B, also rank 3 is sending to itself. There's nothing wrong with sending to yourself, except you have to worry about deadlock. So how can I fix that? How can I send data from rank 1 to rank 3? What do I need to do? How can I make sure that only rank 1 executes the send? It's just a piece of and absolutely, it's just an if. You just say if rank equals 1. Okay, so if this is the problem. Well, this is the issue with MPI programs. Unless you say otherwise, everybody does everything. Okay? So you need an if. Okay, so in particular, all your print statements in MPI are protected by if. Typically, okay, I'll come back to that. Now, if you want to send a scalar, the prototype expects a pointer to an array. So what you do if you want to send a scalar is you just say int x1. If MPI send, you do the address of x and say it's 1 integer. Okay, so that's just normally for an array you just do x, but if it's not an array, you take a pointer and say it's an array of size 1. It's fine. Okay, is that clear? Is people happy with that? Any questions on that? Send and receive are not as simple as in MPI as a lot of people make out. It is not trivial how send and receive work. Somebody's already asked very deep questions like what happens if you send 2 messages and receive 1. I mean, it's not trivial, but it's important to get the basics. Okay. So in Fortran, it's exactly the same. Interarray 10 interdimension 10x. Rank equals 1, MPI Send x10, it's MPI integer, of course. Commonwealth, I have to have an error here. Fortran, unless you're a real Fortran purist, a scalar is just an array. Fortran always passes by reference. So you can get away with just saying MPI Send x1 MPI integer. Okay, so you don't have this subtlety in Fortran about pointers and arrays, which is nice. Receiving a message. Now, when you receive a message, MPI receive, buff count data type source tag com status. So here we are. I want to receive a message. I'm going to receive it from somebody, and it's going to have a certain tag. And I've got an array of maybe 10 integers here, and the data will go into here into the receive buffer, and the metadata will go into we'll go into this status, and we'll see how to declare status later on. Now this is where MPI and so status is a collection of different things. In C, the status is a little structure with half a dozen little entries in it. When MPI was defined, this is where Fortran 2008 differs, and I'll tell you how to use it tomorrow. But in Fortran, because MPI was defined before Fortran had structures or derived types, the status, the prototype's the same: buff count data type source tag com status and the old I error here. But the status is an array of MPI status size integers. This is a number defined in the header. It will be 5 or 6. It's a small number. So the status in Fortran, the status is a small integer array. The number 1 error in Fortran is to say status is an integer instead of an array. The technical reasons, the compiler probably doesn't pick that up as an error, and you get runtime problems. So number 1 error for Fortran programmers is to forget to make status an array. That is the number 1 error. So let's see some examples. So I want to receive data from rank 1 on. So remember previously, what did we do? We sent data from rank 1 to rank 3. Now we want to receive data from rank 1 on rank 3, so I declare my receive buffer in y10. I declare my status variable, which is of type MPI status, but it turns out in C to be a little structure. And I do MPI receive y, it's 10 integers. Okay, I want to receive from 1. You have to specify the tag as well. The sort, and we'll come back to the source must match and the tag must match. Communicator and then the status. You have to pass the address of status. Okay. And again, for a scalar, again, I have to say if rank equals 3, because by definition, if I ran that code, everybody would receive and it would deadlock because everybody would be receiving and nobody would be sending. And again, for a scalar, you just specify address of y and say it's 1 integer. Now, and I'll do the Fortran one next because it's just the same. Again, dimension 10y. So this is the difference. In C, it's MPI status. In Fortran, it's integer dimension MPI status, size status. It's one of the few places where there's significant difference in the syntax. And as I said, it's purely historical. Call it y10 integer 1, 0, MPI com status IR. Again, for a scalar, it's just the same. So, what do you think this 10 means here? It's not obvious. This is not a trivial question. MPI receive y10 integers. What does that 10 mean? It could mean a number of things. What do you think the 10 means? No, sorry. So it is the count. So this 10 is. So I'm saying MPI receive is the count. So I'm saying I'm going to MPI receive. Okay. So Declan said size. What do you mean by size? This is not a trivial question. It's just I want to see what people think it might be. Size of what, Declan? Just out of interest. So Camille thinks it's the number of elements received. Declan, Super thinks it's the size of the array. Okay, so it's not obvious, but technically, it's the size of the receive buffer. It is not necessarily the size of the incoming array. So in many programs, they're the same. But what you're actually saying is, I'd like to receive a message from rank 1, okay? And by the way, I have a receive buffer of size 10 integers. Okay. So for example, you can imagine many situations where you don't know how many elements you're going to receive. So for example, imagine I was doing, you can just think of a lot of situations where I want to send you 5 elements, but you don't know you're receiving 5 elements. So MPI wants to let you write programs where you can receive messages of unknown size, because that gives you more flexibility. Yeah, that makes sense. Otherwise, you'd have to send the size first, and then it should be 2 messages or whatever. If the incoming message is larger than status, then that's an error. Okay, turns out. But the incoming message could be smaller. So if this, so yes, so that's the next. So a good question. How do you actually check the length of the message that we are receiving? Well, I'll come back to that. Okay, it's in a couple of slides' time. So in synchronous blocking message passing, the process is synchronized because the sender specifies the synchronous mode, MPI Send. Blocking both processes wait until the transaction is completed. I will discuss MPI Bsend and MPI Send in the next lecture, but I prefer you to understand exactly what MPI Send does. And the important point about MPI Send is that if the send is early, then the receiver, if the send is early, then the sender waits. If the receive is early, the receiver waits. MPI, to a large extent, is written so that it doesn't matter what order things happen. The synchronization works correctly for you. So for communication to succeed, the sender must specify valid destination rank. Obviously, the receiver must specify valid source rank. The communicator must be the same. We'll come back, but communicators are guaranteed, are communications worlds. So a message is guaranteed to be ring fenced inside the communicator in which it was sent. But if you use MPI com, well, that's fine. The tags must match, the message types must match, and the receiver's buffer must be large enough. If the receiver's buffer is not large enough, then there is an error. Now, you might think, however, that there's a bit of a double counting here. For the send to, so I said that you could specify extra information in the tag, okay, but I'm saying that to receive a message of a tag, you must know what the tag is. So that's kind of crazy, yeah? And also, both the communicator and the tag must be the same. So that looks a bit weird, but the point is you can wildcard. So you can say receive any tag. And in practice, tags are only useful if you receive with any tag. You say, you do MPI receive MPI any tag, and then the actual tag value is stored in the status parameter. Or you receive from MPI any source. So for example, if I had one of these controller worker situations where I'd sent all you guys out lots of tasks to do, I might say, I want to wait for someone to finish, receive your result, and give you some more work. But I don't know who's going to finish first, so I issue a receive with MPI any source. The first person that sends it, I match, and then I look at it and say, who is that from, by checking the tag, and then I can get back to you. So the status contains the information on the actual message which was received. And so this is like the communications envelope. You know, there's the address and things like that. The major part of the message is the payload, the data, but you know, there's who it's come from, where it's going, such like as well. So so the status in C, these are direct elements of the structure. The source is status.mpi source. The tag is status.mpi. Remember, these are filled in when the receive completes. In Fortran, remember I said status was a little array, which might be, I don't know how long is 6. It might be, the status might be the third element of that array, in which case MPI source would be 3 in the header file. You shouldn't assume that, but all it's saying is, you know, this element of the array, which might be the third or the fourth entry, contains the status. Status of MPI tag contains the tag value. So in C it's dot, and in Fortran it's a member of the array. Now, Michelle asked, how do we know how long the what did Michelle ask? How do we actually check the length? That is stored in the status, but it's not directly available. You have to pass the status to a helper routine called MPI get count. So MPI get count, you pass it a status, and you say how many integers, for example, were in this, and it will tell you. So you can inquire, you can say, look, I just got this message, it's got this status. You can ask MPI, how many integers was that? And it will tell you it was 5 integers, for example. So to answer Michelle's question, to actually check the length of the message we are receiving or have received, it's stored in the status, but it's only available via helper routine. It's not directly available as an element in the status. The reason is, you can think of it that MPI only knows how many bytes okay, so okay, fine. So there is a routine, I'll cover it later, called MPI probe. So MPI probe tells you everything about the incoming message without actually receiving it. So MPI probe gives you the status without giving you the message. So you can say, what message would I receive if I should receive? Then you can allocate the data, and then does that answer your question? So that's okay. So if you want to do that, you need to use MPI probe, and I cover that briefly in the next in somewhere else. So what happens to training elements if you receive side? That's a good question. I'm not going to answer that because that's one of the questions I ask in the quiz, because it's not obvious, and I like people to know what people think. So sorry, it's a very, very good question, but it's so good that it's in the quiz, and I'd rather hear what people have to say. Very good question, though. Good question. So as I said, you can imagine this as saying, actually, MPI only knows it received 16 bytes. That could have been 2 doubles, 1 double complex, or 4 integers. So that's almost completely true, but it's a slightly subtle point. But anyway, so it gets quite technical, message order preservation. So what I'm going to do, there are some detailed slides here on message order preservation, but I'm not going to go into them because you can come back to them if you want. But you can imagine, okay, that if you use non-synchronous sends like MPI Bsend, you can issue lots and lots of sends before any receives. Okay. Now it's like sending a letter, okay, or postcard. If I'm on a holiday, yeah, I can send 5 postcards back to my mother. If I send 5 postcards in order, okay, our postcards is postcard ordering guaranteed. No, it's not. However, it's not. However, MPI guarantees message order preservation. Now, it's slightly subtle because, and that's what I'm going into here. But the important statement, and I don't want to go into this because we're running, it's a lot of lectures today. Is the correct statement is, if a receive matches multiple messages in the inbox, then the messages will be received in the order they were sent. Okay, that is, and this is when if you think about there being an inbox. So that, and it is actually very important. It may not be obvious, but maybe in a couple of days or weeks, think about it. If you did not have message order preservation, it would be very difficult to write a correct program. You might have a situation where you send lots of messages and then you send a termination message, I've finished, but that termination message could overtake the other messages. And so, so actually, without message order preservation, it's very difficult to write a correct program. Or challenging. So we take it for granted, but actually message order preservation is actually quite important in MPI. It's only relevant for multiple messages from the same source. This is message order preservation between communications between one sender and one receiver. MPI doesn't guarantee anything about what happens with messages coming from multiple sources. It doesn't actually make any sense to talk about that. But if you have between a sender and a receiver, the messages will be received in the order they were sent. So that's if that's okay. So where they live depends on how what the MPI implementation does. You don't actually know. It depends. I mean, you can think of them as living in an inbox. It depends. So we will cover something called non-blocking communication tomorrow. Well, I will cover. So I will cover that to a certain extent in the next lecture. At least for buffered sends, I will talk about that explicitly. For non-blocking operations, which we'll talk about tomorrow, it's different. But hopefully, if you wait till the next lecture talks about where buffered sends live. Is that you? So that's what I'm going to talk about in the next lecture. Yeah. Okay. Here's a question though. I'm on holiday. And I want my mother to. How can I make sure my mother reads? How do I make sure that if she gets a postcard, she can say, oh, actually, they sent one before this which hasn't arrived yet, so I won't read that. I'll read the next one when it comes in. Read my postcard. How can I do this? Number. Exactly right. So timestamps aren't enough because my mother gets a timestamp and it says David sent this on the 3rd of January. The last one. How do I know? So Declan's right, you number them with a monotonically increasing number. So you number your first one 0, then 1, 2, 3, 4. So she reads postcard 3, that's fine. Then she gets a postcard which is 5. She knows that I must have sent a 4 in between. Now, what Alec is saying is very interesting, that actually, if you didn't have message order preservation in MPI, you would have to use tags to do this. You would have to tag all your messages with a monotonically increasing integer. You don't have to do that because MPI maintains message order preservation. But if I was doing it on postcards, I'd have to say this is postcard number 0, and dates aren't enough, because as I say, I sent, if my mum gets an email, a dated one, she doesn't know if I sent one. I might have sent 2 or 3 on the same day, or I might have not sent a message for a month. So it has to be a numbering, a predefined numbering. So are there any other questions? So normally in the face-to-face thing, we would go on to the calculation of pi, but we won't do that now. But what I will do is I will spend 5 minutes describing the exercise, then we'll have a 5-minute break, or 5 or 10 minute break, and I'll give the next lecture, and then we'll have the exercise from half 3 to half 4. So final thing, my example is by far the most important example. There is a ping pong example which is used to measure how fast the network is. You send a message from A to B and back again. It's like playing table tennis, ping pong. You need to time the program. So in MPI provides with a timer, which is a double precision, and this is measured in seconds. So you basically do a time, start time is MPIW time, and then end time is MPIW time, and then you subtract them. It's just, again, 30 years ago, there were no standard timers, so MPI provided a timing routine. So I'm going to now basically, so you can send derived types, yes. Mark will give the lecture tomorrow, which tells you how you can send, for example, a structure. Or are you a Fortran program? Sorry, do you mean, there's a slight confusion in terminology? Yes, so MPI has something called derived types, which correspond to C structures or Fortran derived types. So you can do it, yes, but you have to define them yourself at runtime, and there are routines to allow you to do that, and Mark will cover them tomorrow. Is that okay? But we want to, fine. So if I just basically, again, go to our old friend, there's only a single exercise sheet for the whole, which is this guy. So, oh, I have to stop tonight. I get very confused easily. So assuming you've done the hello world, right. So an approximation to the value of pi can be obtained from this expansion. This is just the integral of, is it arc tan x is pi by 4? Sorry, integral of 0 to 1 over 1 plus x squared is arc tan x. So an arc is pi by 4. Okay, so this is just, and this is a very, very simple approximation where I've not even done the trapezium rule, I've just added it up. So this, but just believe me, pi by 4 can be approximated by this expansion here, okay, where the answer becomes more accurate with increasing n. So iterations over I are independent, so the calculation will be parallelized. What we're going to do, set n equals 840. So this is divisible by 2, 3, 4, 5, 6, 7, and 8. So that's easy to calculate. What we're going to do is, if we were running, for example, so first of all, modify your hello world program so each process independently computes the value of pi and prints it to the screen. Please check you get the first answer right. It's very easy to get this wrong. C programmers, that loop starts from 1, right? That's not 0, that starts from 1. That is 1 to n, okay, not 0. Check, you should get 3.14159. You should get a decent value of pi, okay? And then arrange for the different processes to do the computation with different ranges of I. As I said, on 2 processes, rank 0 would do I equals 1 to n over 2, and rank 1 would do n over 2 to n over 2 plus 1 to n. We then print, and that shows you how to divide up computation based on rank and size. You print the partial sums to the screen and check the values are correct by adding them up. by hand. So then you've checked that you've split the calculation up correctly. Now we want to add them up using MPI. So we want to accumulate these partial sums by sending them to the controller rank 0. So all processes except the controller send their partial sum to the controller. The controller receives the values from one of the add them to its own partial sum. Now, if you were actually going to do this program in practice, you would do this part using a reduction operation, MPI reduce. But it's actually a very, very good training exercise. This is a surprisingly difficult program to get correct. It illustrates a lot of issues. So use MPI send and MPI receive. And if you want to, you can time it and stuff like that. But you know, this is the key example, okay? Parts 1, 2, and 3. So that's what we're going to do. And what I'm going to do now is take a 10-minute break, say, then come back and give the communicator tags and modes talk. We've talked more about some of the issues you've been asking about where is the data actually stored, what happens if you send more than one message and it's not received. So that's what I'm going to do. Does any other questions? So you can start working on that if you want, you know. And if you have any other questions, just ask them, and I will now. It's up to you. You can start the exercise if you want. I would recommend you take a break to clear your head and come back. But you're welcome to the exercise if you want. You're welcome to start the exercise. But the whole session. Going on here. I'm wrong here. So Monica's asking, where do I have the solution for the exercise 1.1? So if I show you, that's a very good question. I need to stop sharing again. So can you see the X? Yes. So if you look down here, we have simple subsets for the exercise. Do you see that there? Okay, so I should get my laundry done. So I shall now, let's check that we're doing the right thing. So I'm now going to share the next lecture, which is last lecture for today. This one. check. Can you all hear me okay? Just great, okay. So this lecture is called Modes, Tags and Communicators, and I'll explain what it is. So what this lecture will cover is the explanation of MPI modes. An MPI mode, MPI means whether it's synchronous, Send, buffered or asynchronous, Bsend, or standard MPI send. Now, it is surprisingly complicated how this works. So that's, I mean, I didn't understand this for a long time. And I was lucky because in the early days of MPI, there was a group at EPCC that wrote MPI libraries. So I could go and ask them, you know, what's this all about? But it is actually very important to understand this. And this is probably the difference between Send, Bsend, and send, between synchronous, asynchronous / buffered, and standard send, is probably the most commonly misunderstood thing in MPI. So excuse me if I go on about it a lot. I'll talk a bit about tags and communicators, but these are all commonly misunderstood. But it's essential for all programmers to understand modes. To write correct programs, you need to understand modes. It's often useful to use tags, and you know, and there are certain situations where different communicators can be useful. But this lecture is largely about the modes. So just to recap, you've got three choices of modes. Sensible choice anyway. MPI send, synchronous send, guaranteed to be synchronous, routine will not return until the message has been delivered. And that's why when you program in this course, I would recommend that you use MPI send, at least for developing programs. We can come back to this later. MPI Bsend is buffered send, it's guaranteed to be asynchronous. The routine returns before the message is delivered, and the only way this can be implemented correctly, if you think about it, is if the system copies data into a buffer and sends it later on. Now, you might think surely buffered send, asynchronous send is by far the best thing to do, but I'll explain why it isn't in practice. MPI send, standard send, may be implemented as synchronous or asynchronous. You've no idea which. Well, in principle, you've no idea which, and this will cause a lot of confusion. So that's what this lecture is about. It's basically going to tell you why MPI Bsend is a bad idea and why MPI send was implemented the way it is, when in fact it looks a bit crazy. So let's do the anatomy of a send. So MPI send, process A and process B, time is going down the way. Okay, so time is going down the way. Process A and process B. So process A issues an send of X to B. Now, I am going to assume here that the send is issued before the receive. I'll discuss later on the inverse, but this is the interesting, and this is the situation which illustrates the point most effectively. At this point, process B is running some other non-MPI code. So at that point, what does process A do? So it issued synchronous send. Exactly, it waits. So process A waits in the send. Now, if process B carried on, okay, so it's actually quite important here. I'll make two points here. When you're not calling MPI, it's just a program. It's just running. It's like any other program, okay? When you're not calling MPI, a program's a program. It's just sitting there running away, adding numbers, doing stuff, okay, reading and writing files. It only becomes it's only really a parallel program that's calling MPI routine. The other point is that actually MPI has to be designed to be correct, regardless of whether, I'm going to discuss later on what happens if process B, so here process A is faster than process B. Process A gets to the send before process B gets to the receive. But you can imagine process A might be slower. The point is you have no control over the speed of process A and process B. Okay, so MPI has to be correct regardless of whether process A or process B is first or second. Because process A is running on my laptop here, process B is running on my colleague's laptop in Australia. Who knows how fast her maybe she's playing Call of Duty on a laptop, and so her MPI process is running really slow. You know, you have no control over the mutual timing of how processes, what order they run it, unless you do explicit communication. Okay, so people often like to think that all their MPI processes are chunking through line by line at the same speed. Nothing could be further from the truth. You've no idea. One of them could go to sleep for half an hour for all you know. So I mean, that's extreme, but you have no control over the speed of how they actually run, how fast they run. Okay, so hopefully, if it's a correct program, process B issues a receive. It says, look, this is an abbreviated syntax, but I want to receive data from from A, and I'm going to put it into Y. And at that point, the data transfer happens. It's called synchronous send because there's a synchronization in time, okay? And if you think about it, this could happen with no copying, because A and B are both on the lane. Like A says, I've got this data for you, and process B says, I want it here. So you could just put it in the right place. What the send returns, then the receive returns. When the send returns, the important point is that you can overwrite X can be overwritten by A, because you know it's been sent, because synchronous send, it means when the synchronous send routine returns, the data has been transmitted. So you can overwrite A and carry on. And when the receive returns here, so yes, it does use the same. What do you mean by the? So that's an interesting question. So I mean, the data starts out in X and ends up in Y. And in principle, that could be done without any copying. There might be copying, but in principle, it could be done. I don't quite know what you mean. It's an interesting question. I don't quite know what you mean by the same memory location. I mean, A sends the data. Yes. Oh, no, because when I say copying, I mean no explicit intermediate. I mean, it's not a pointer because A is on my X is on my laptop here and Y is on my colleague's laptop in Australia. So it needs to go down the wire. What I mean is, it doesn't have to be explicitly copied. You know, I don't know about net, but you know, the net, you know, the data. Maybe I'm making. There's no explicit copying. Does that make sense? You know, it could just be. I don't know how networks work, but you could pump it in one end of the network and it'll pop it out at the other end. Yes. Oh, yes. I mean, sorry. When I say copying, yes. Sorry. This is maybe. I mean, no intermediate buffering. So the data is copied from X on A is copied to B on Y. But what I mean is I might say single copy. When I say no copying, I mean I know no additional copying. There's one copy or network transfer going on. Sorry, I understand the confusion. Sorry. When I say no, I see no intermediate copying necessarily. Yeah. And so it is like it's like reading a letter. It's like speaking to somebody down the phone rather than transcribing it. And that's, I'm taking that analogy too far. When the receive returns, that means that the data has been received, so that Y can now be read by B. So there are two bad things about this. Two things you might not like. A, there's a lot of waiting around here, right? Process A is doing a lot of waiting around. We don't want programs to wait around. We want them to do stuff. And B, if we never issued a receive here, the program would deadlock because process A would sit here forever. So you might think, well, let's use Bsend. Let's use asynchronous send. So here we go. Process A issues a Bsend of X to B. Process B is issuing some other non-MPI code. Remember, Bsend is asynchronous. It's a fire and forget. Okay, it's just send the data. So what MPI has to do is it has to take a copy explicitly on process A. Okay, so there is a copy is taken on process A. Okay, and then so the Bsend returns whenever a send operation completes. You can overwrite the send buffer. If it's synchronous, it's because it's been transferred. If it's asynchronous, it's because it's been copied. But when a send routine completes, regardless if it's synchronous or asynchronous, you can always overwrite the send buffer, which is nice to know. Okay, otherwise it'd be hard. And so at that point, A just carries on. So we've eliminated the waiting, which is nice. Well, we've now got a copy here, but we've eliminated most of the waiting. Now, if process B didn't issue a receive, the program would still run. It might not be correct, but it would still run. There'd be no deadlock. But hopefully, process B issues a receive. At that point, the data transfer takes place. Okay, there's no synchronization in time. Then, presumably, this buffer is freed up. And then, so we've achieved the same thing. The data X on A has been copied or transferred to B on to Y on B, but we haven't had all this intermediate. But it's a very simple question. But where does this buffer come from here? And the problem is that it's a slightly technical point, but the way that MPI is designed, it has to operate within a finite memory footprint. It cannot use infinite amounts of memory. So I'm about to answer. So you've got exactly you're exactly on the right. That's exactly the problem. Camille, that is exactly the problem. So MPI says that. Well, the MPI standard says that MPI cannot take an infinite amount of memory. It has to have a manageable memory footprint. So what MPI says is, for buffered sends, you, the user, have to supply this buffering space. So it's a bit weird, but what you have to do... Now, actually, I'll just, before I come on to that question, I'll say receive is always synchronous. So if process B issued the receive before the Bsend from process A, then B would wait in the receive. So in fact, the reason I've drawn it this way is if B issues the receive first before A, then Bsend and synchronous send look similar because B waits around until the send happens. So that's why I've written it this way around. The receive happening after the send illustrates the point more clearly. But the question is, where does the buffer space come from? So MPI says, okay, I can't guarantee to buffer them. So you, the user, have to say, give me memory. So there's a rather nasty routine called MPI buffer attach. So the idea is you say that in this program I'm going to do asynchronous sends. I'm going to want you to buffer messages. Okay, I'm going to malloc or allocate a megabyte of memory and give it to you. It's called MPI buffer attach. It says, look, an MPI should then use that space to buffer messages. Okay. So it's up to you to give it the message. But the problem is, okay, imagine I've allocated, well, here's two things, okay? I want to send a megabyte of data, okay? So I have to give it the space to copy the data here, okay? So if I want to send megabyte messages, how much memory does it need? I mean, it's a slightly tricky question, but, you know, a megabyte, a bit more. I want to send a megabyte of data. I have to give it enough buffer space to store the whole message. Is that a megabyte? I think it's a bit more. I don't know. I don't have a guess. More. Why is it more? For the metadata, exactly. So there's this horrible. So you have to allocate. The reason I'm not going to I should jump to the chase. Nobody uses Bsend, okay? Although it sounds like a good idea, people don't use it. But what you have to do is allocate data plus MPI Bsend overhead bytes. Okay, so you have to add this magic constant called MPI Bsend overhead, which, as if you pointed out, is for the metadata. Fine. Okay, I've done that. That's okay. Fine. So I've allocated 1 megabyte plus the Bsend overhead. That's fine. What's the problem? What's the next thing that process A can do? Okay. What's the very next thing it could do? I've got it doing computation, but what could it do? What might it decide to do? It could overwrite X, but that's okay. Well, it can't overwrite X. Well, it can overwrite its own X, but not this. That's not what I'm getting at. But yeah, that's probably true, but I'm not quite what I'm talking about. I've got it going away and doing computation, but it could do something else immediately. Issue a second send, exactly, a third, a fourth, a fifth. If process B was having a bad day and was really slow, it could, in some cases, it could issue an almost who knows how many sends. It's like filling up the letterbox. Now, in some programs, you can reason that A could never send more than, but it can be quite difficult. So the problem is you can get a program which runs correctly, okay, but once in a blue moon, process B is having a bad day, is very slow. So process A issues 3, 4, 5, 6 sends, and MPI runs out of space. And it says, I'm sorry, I can't do it. You've told me to buffer this message. I've run out of space. And it will crash and burn. And just say, can't do it, and it will crash, like MPI always does. When it has a problem, it crashes. So it is quite difficult. It's ugly to use. And it can be difficult to work out how much buffer space you need. If you get it wrong, you can get a program which works sometimes and not another time. It's nasty. And so we tend not to use. So if we said, if A issues another Bsend before the receive, the system tries to store the message in the free space in the buffer. If there's not enough space, then Bsend will fail. So what you would like is to use Bsend because they get rid of all this nasty waiting around, but it's hard to mandate that MPI uses the Bsend because it's hard to make sure that it has enough memory. So here's the problem. Send runs the risk of deadlock, plus you get this waiting around. Bsend is less likely to deadlock and your code may run faster, but the user must supply the buffer space. The routine will fail if this buffering is exhausted. MPI send tries to solve these problems, okay? MPI send provides buffer space. So that's a very good question. Is there a way to check if the buffer is empty and ready to be written? A lot of people have asked that, and no, there isn't. I don't think. It's a very good question, actually. The reason why it isn't is actually people don't use Bsend. But actually, if they did, they would want exactly that. But actually, well, MPI send solves that problem for you. Okay, so what MPI send does is it says MPI will reserve some buffer space. This isn't it will say, I don't know, a megabyte. I don't know. So each MPI library will have some buffer space it reserves. When you call MPI send, MPI will try and buffer the message, okay? But if it can't, it will check. It will do what Michelle is suggesting. It will check. If it can't, yeah, rather than failing, it will say, I don't have enough buffer space to do an asynchronous send. It will just become synchronous like Send. So the rationale of MPIs is don't tell MPI whether to be synchronous or asynchronous. Call MPI send and let MPI decide. Let it do the best thing, okay? That's the rationale. That's the party line, okay? The problem is it causes a lot of confusion because you don't know what MPI is doing at runtime. But you're absolutely right, Michelle. I don't believe this can be done manually. In fact, you're not the first person to ask that question, but no, I do not believe it can be done manually. It's a very good question, but I don't think it can. I'll check up, but I don't believe it can. That's a very good question. How do I play an API Bsend overhead in Fortran? I would. That's a very good question. So what I would do is probably, let's say, something like it's nasty. Yeah. That's a hacky, but see what I'm doing? I'm rounding. I'm allocating Bsend overhead divided by 4 ints, which is Bsend overhead bytes, but I'm rounding up because in case Bsend overhead is 3, for example, it rounds up. Does that, I mean, it's kind of horrible. You see how horrible all this stuff is. That's why, you know, does that actually answer your question, Christoph? You're right. Is there a method? There might be. I should look at. The thing is, I don't know. I tend not to use. That's what I would do if I was told to do it. I would do something horrible like that. But then I'm an old-fashioned, horrible Fortran programmer. No, no, no. I don't believe so. No, no, it doesn't. It just says, trust me, it got there. Yeah. So here's the problem. So in practice, yeah, if you use MPI send, small messages are buffered, big ones aren't. Okay. So if you send an integer, it will be buffered, it'll be fine. If you send a gigabyte, it won't be. It'll be synchronous, and there'll be some threshold in between. That's what happens in practice. Okay. However, this is the problem. Okay. Imagine this code. Okay. Process A does send xb and receive xb. Process B does send ya, receive ya. This code is not guaranteed to work. You have to understand, if you used send here, okay, if you used send here, this program will be guaranteed to deadlock, because process A will be saying, I'm going to deliver a message to B, and I'm not going to do anything till it's received. Process B is doing the same thing to A. They're both phoning each other and wondering why they're not picking up, okay? So it's very important to realize, you have to realize that this code is guaranteed to deadlock with send. Therefore, it might deadlock with send, right? It might deadlock. And so this is a very, very dangerous program. It's a program which might run and might not run, okay? Depending on the time of day or what MPI library you're using. So that is why I say when you develop MPI codes, use synchronous send, because you know what it does. And if you write a wrong program, it will not work. When you write an incorrect program, you want them not to work. You don't want incorrect programs just to happen to work. I always say to people, you know, I could close my eyes and cross the road without looking. Okay, I might be lucky, but it's not a safe thing to do. Okay, you know, just because you get away with it. So that's why I say program with send. So you should always assume that the worst case scenario with send. The worst case scenario is that the message is synchronous. It's not buffered, so you have to cope with that. So how can I get this to work? How can I get this to work rather than having A send? I've got A send receive, B send receive. That is guaranteed to deadlock with send and might deadlock with send. How would I fix that in this particular instance? How could I send the data? I'm doing a mutual exchange, A to B, B to A, and I'm trying to do the sends first, then the receives, and so it's potentially deadlocking. How could I fix that? No, with imagine I was using synchronous send. Imagine I'm using synchronous send. How can I use synchronous send and exchange the data correctly? I'm maybe not asking the question quite correctly. So the problem is that A is sending, then receiving, B is sending, then receiving, so that, yes, exactly. So you swap one. So A could send, receive, and B could receive, send, okay? However, so the basic problem we have here is we can't have more than one send outstanding at once or more than one receive outstanding at once, okay? So we have to order them. That is okay for pairwise exchange, but it doesn't generalize. And okay, so to avoid deadlock, you either match sends and receives explicitly. For ping pong, A sends and receives, B receives. However, this is such a common situation. The general solution is called non-blocking communication. So tomorrow we will cover non-blocking communication, which is the general way to solve this problem, okay? And it allows you to have multiple operations at once. You can tell MPI, do these 15 sends and these 15 receives for me. The problem is with the way we've talked about at the moment, these blocking up, they don't return until they're complete. So it's slightly, but for this course, you should program with send, more likely to pick up bugs such as deadlock than send. So develop program with send. Once they're working and correct, you can change all the sends to sends, and it might run faster. But you know, I think you should program with send. If you program with send, it's very easy to write incorrect programs that happen to work like this one. So it's unfortunate I have to talk about all these details this early on, but it is the most confusing thing about MPI. the standard send, which would be, if I was teaching you MPI, you say, how do I send a message? I'd say, use MPI send. Is it synchronous or asynchronous? You don't know. And that's just the way it is. And you need to understand that and be able to cope with it. Now, once you learn about non-blocking communications, all these problems go away because you can solve all these issues with one fell swoop. But it's not trivial. It's not it's worth thinking about, and we can maybe come back and talk about it when you've had a chance to think about it. But I didn't understand this stuff for quite some time. So if there's any more questions on that, I'll just quickly talk about. Okay, so someone asked before, checking for messages. MPI allows you to, I never quite know where to put probe. MPI allows you to check if any messages have arrived. You can probe for matching messages. It's exactly the same syntax as receive. External don't receive. So you're saying, if I issued a receive here, no, you can't. You can only send or receive. You can't. No, you can't. So a lot of these things that you for example, you're asking me, you would want to do in a general, if you had a very general free-form network, if you were writing, I don't know, a Twitter client or something like that, you need all these, you need all these functionality. MPI is really quite restrictive because it was designed specifically for scientific and technical computational science. So it's very much, you send a message, you receive it, you send a message, you receive it. And a lot of the things you're talking about, which are very useful things to do on the if you want to do much more free-form, fault-tolerant, general purpose kind of, flexible things, MPI is maybe not for you. But MPI is really designed to map onto what you want to do for large-scale, high-performance computers, computational science or data processing codes. So it maybe doesn't have all the functionality you'd expect of a fully fledged network protocol, but it's because it's deliberately simple to allow it to be optimal, fast for sending data. Yeah. Probe is just the same as receive, except there's no receive buffer. The status says as if the receive took place. So you can do a receive, look at the status and say, if I issued a receive here, who would it come from? What would the tag be? And how big is it? How big is the message? You have to be careful with wildcards. If you use MPI any source, okay, you can't do MPI probe any source, MPI receive any source, because it's not guaranteed those two any sources are the same. So you have to do MPI probe any source and then MPI receive status dot MPI source. It's just a technicality, but no, people have asked about that before. Tags, every message can have a tag. This is a non-negative integer value. Tags can't be infinitely large. A lot of people often think a tag. So Monica, can I cover that just at the end of this lecture? That's a very good question. I will. That's a very good question. So tags have to be non-negative, i.e., 0, 1, 2, 3. A lot of people assume, oh, they can be as big as you want, like 2 billion. They can't. MPI guarantees to support tags of at least 32,767. Most MPI implementations will support tags of millions, but they are not infinitely large. If you're really worried, you can query. You can say to an MPI library, what's the biggest tag value you are allowed to put MPI tag UB? But you should assume that the tag cannot be infinitely large. So we sometimes get problems where people have programs where the tags go into the billions, and it works with one MPI implementation, not with another. But not everyone uses them. You have to specify them. I very rarely use them. I often set all tags to 0. Some people, if you're not using wildcards, then tags are of no use really. Okay, I mean most commonly use them. So for example, in this controller workers thing, I'm sending you guys work. You're sending me results. I need to tell you when to stop. So what I would do is I would send you a message with tag 0 is stop, or tag 1 is there's going to be more work, okay? Or tag 0 is this is a stop message. Tag 1 this is a payload message. You, the receiver, would do MPI receive from 0 with tag MPI any tag, and then look at the actual tag and say, oh, he sent me a 0. I should stop. He sent me a 1. You could do this extra messages. You could send, but I mean, it's more efficient to use a tag. Communicators, all MPI communicators take place with a communicator. A communicator is fundamentally a group of processes. There's a bunch of predefined communicators. Predefined MPI com world contains all the processes. MPI com self contains only you. The important point is the message can only be received within the same communicator from which it was sent. So, and this is different from tags. You cannot wildcard on com. You can wildcard on tag, but you can't wildcard on com. And so tag different communicators is an absolute guarantee that messages are kept separate. So there's a couple of uses of them. The first one, which people often think about, is split MPI com world into pieces. Each process has a new rank within each subcommunicator. So there's a routine called MPI com split you can look up, which allows you to split a communicator into two pieces. So if I com world had 7 ranks, I could split them into com1 and com2. Com1 might contain ranks 0, 1, 2, and 3, and com2 might contain ranks 4, 5, and 6. However, these have different sizes, and within this communicator, your rank is local to a communicator. So, for example, ranks 4, 5, and 6 become a communicator of size 3. Within com2, your ranks are 0, 1, and 2. Within your rank is specific to a communicator. So within com2, this guy is rank 0, but in com world, she's rank 4. So if you're going to play around with splitting up communicators, then you need to be careful that you recompute your ranks within the subcommunicator. But these guarantees that messages within this communicator cannot be received in this communicator. You might say, I'll do it myself. I'll not use communicators. I'll just send. So yes, I'll come back to that. That's an important point. Right, that's a very good question. I've lost my thread. Sorry. You could just say, look, these guys will use tag 5 and these guys will use tag 6. It'll be fine. No, but you could use MPI any tag and it could wildcard. So that's care. So yes, so you might imagine a model where at MPI you say, please join this communicator, join that communicator. No, every MPI communication routine, send or receive, takes a communicator. So you are simultaneously a member of many communicators, but you decide which one you're using in each send or receive. That's the model. So yes, you are present in multiple split communicators. So I am both a member. This guy here is both a member of ComWorld and Com2. They can decide every send. I'm going to send in Com1, I'm going to send in Com2, I'm going to receive in Com1, I'm going to receive in Com2. Does that make sense? So you're simultaneously a member of multiple communicators, and which one you use, you can decide on each send and each receive, you specify a communicator. I don't know if that makes sense. The other use of communicators is to actually make a copy of ComWorld. So if you just say MPI com equals MPI com world, it's the same communicator. There's an MPI com dupe routine which duplicates a communicator. So you can duplicate MPI com world and produce a new communicator that contains all the same processes but in a new communicator. So here you have a communicator of rank of 7. You also have another communicator down here. They're separate communications worlds. Okay, they both contain all the processes, but they're separate communications worlds. And the reason you might want to do that is to write a library routine. Imagine I've got fast Fourier transform. Imagine I had a parallel sort routine. I wrote a library routine which did a parallel sort, did a very fast parallel sort. My parallel sort routine is going to be sending lots of messages. How do I make sure that there is no way that the user can inadvertently or deliberately intercept them? The first thing the library routine does is it creates a new communicator which contains all the processes but is private, and it uses that to send the routine. So it allows you to have a separate communications world. So one of the other reasons that communicators were introduced was to allow you to write efficient library routines. Safe library routines. So summary, why bother with? I'll answer the outstanding questions in a second. Yeah. Why bother with all these send modes? Answer, it's a little complicated, but you should make sure you understand Send and Bsend are clear. They map directly onto synchronous and asynchronous, but Bsend's nasty to use and people just don't use it. Send can be either synchronous or asynchronous. MPI is trying to be helpful here, but it does lead to endless confusion. the amount of system buffer space is variable. So in practice, if you use MPI send, small messages are buffered, large messages are sent synchronously, but you should never assume that. And as I've said before, you might be then thinking, how do I write deadlock-free correct programs? Well, you use non-blocking communications, which will be the subject of tomorrow's lecture. What are all the tags for? If you don't need them, don't use them. But some people like it for debugging. I rarely use tags. I normally set all tags to 0. I don't normally use tags, I have to say. And finally, question, can I just use MPI mode? Yes, many people never need to create new communication in MPI programs. However, it's bad practice to specify MPI mode explicitly because, this is a horrible, big, ugly constant. And so it's much nicer to say MPI com equals MPI world, MPI right com. So this is identical to putting MPI mode explicitly here, but it's neater. And also it means later on, if you want to reuse this code for something other than world, you just do com equals MPI subcommunicator here and it works. So it's bad practice to write MPI world everywhere because it's such a big, horrible, ugly constant. The exercise is the Pi exercise, but there was one outstanding question which I think was from Monica. So you asked about documentation. So why don't I just kick up a web page, a website or something like that. Let's do that one. So it depends what you want. If you want a list, you can go to the MPI document and well, it's now up to MPI 4. Let's look at MPI 4. Oh, well, let's do MPI 3. Unofficial MPI 3.1. This has everything here. And in fact, at the end, there's probably where's the index? There we are. Oh no, that's the constants. There's a list of functions somewhere. Not so familiar with the HTML version. It's a bit weird. Anyway, this is the. That's not that. Okay, this is misformatted, hasn't it? But that does contain them all. But it's just a verbatim list. It's not really for reading purposes. There's also what I would say as a colleague of he's a PhD student. Well, this is this is the official version. Okay, this is the official MPI standard, which is the definitive definition of the standard. Not necessarily the easiest thing to read. Okay, it's like if you want to learn French, you wouldn't get a French dictionary. You buy a French, you go on a French course. So, most people use about 15 MPI functions. So I would recommend the book if you want to use the book. A colleague of mine has also developed this site called Rookie HPC. This is Ludovic Kennedy, who's a PhD student at EPCC. And if you go there, box, he has a very nice list of all the commonly used functions and such like. It might be all of them actually. That's quite a nice list. I think that's, and he's got really nice examples. Let's look at MPI send, for example. Let's look at MPI send. Let's find it. MPI send. There's MPI send, and he not only has the prototype. Okay, it's all in C. For our program, I'm going to have to wing it a bit, but also an example here. So, I think that Ludovic's, this is by, I don't know if he actually gives his name here. Okay, Anyway, but anyway, this is developed by a colleague, well, a student at EPCC, and that's very good. It's really up to you. I don't know. I mean, it's not bedtime reading the MPI standard. There are thousands of functions, but you know, I think this is a good one here actually. He has listed it by addressing different terminology. Yeah, I think it's good. Non-block persistent stand. So that reason for sending. Here's the standard one. So there's our. This is MPI buffer attach, which I didn't talk about, but he'll explain it here. You say 4 short examples there. They're meaning on. I don't think Rookie HPC. Do you mean on the Idris one? Oh, apologies. Sorry, yes, I thought so. So where are apologies? I'm doing Ludovic a disservice. How do I? Is it the exercises that he has here? Above the big blue box. God, I'm stupid. So MPI, read more. I'll go to a function. Sorry, God. Let's do MPI probe. Well, no. Sorry. Apologies. No, I think he's very okay. He's very complete. Okay, so there's MPI stand, for example. And so for those of you, while you're here, let's look at MPI receive, for example. I'm going to cover this tomorrow, but it is receive. If you look at the Fortran if you look at the Fortran 90 example, you'll see we have oh, well, he's using MPI status ignore here actually, which is maybe a bit. That's not what I wanted to show actually. Okay, but I'll find another one. But MPI. And the Fortran 90 example, the status is integer status of MPI status size. Okay. In the C example, it's a lot nicer. The status is MPI MPI status MPI status. Okay. The Fortran 2008 just replicates the C standard, so you have type MPI status. So the reason why I only cover the Fortran 2008 example, Fortran 2008 standard very quickly, is it basically replicates the C is MPI status, Fortran is type MPI status, and that is replicated for all of these things. MPI com type MPI com. And so it's really you can just read the C and translate to Fortran straight away. Fortran 2008. Sorry. So yes, Rookie HPC I knew it was very good. I didn't realize it was that complete. But a lot of work into it. Anyway, I will shut up now, and we will come back at. I still have the feeling there was one other question which was outstanding, but I can't see it in the. I can't see it in the list. Yeah, maybe I was just. So we'll take a break now, and it's for the Pi Practical. Just to let you know, I think the Pi practical is so key that if you look at the timetable, tomorrow morning, what I'm going to do is I will spend the first, I think it's half hour just covering the Pi solution, because it's a surprisingly simple example, but it illustrates things very nicely. So I'll kick off tomorrow morning just going through the Pi solution. And I do give fairly detailed, if you look in there are very detailed, or one might say verbose, solutions to the Pi example. Okay, so up to you what you want to do. I'm happy to talk about anything. I mean, it's a practical session. I'm happy to talk about anything. If you want to chat about something else, something which of your own interest, we can go to a breakout room. Now I understand how the breakout rooms work. After I messed up Mark, I know how to do them now. I'd never been in a context before. There were multiple people organizing multiple breakout rooms. I hadn't realized that the end breakout room was a global kill. I now understand how to do it. Okay, so I'm going to have a little break, get myself a cup of tea. I'll be back in 20 minutes.